Good morning, students. Now we start the osmotic pressure. On last lecture, we learn about what is the osmotic pressure, and hence just recall that when a solution and pure solvent of two solutions of different concentration are separated by semi-permeable membrane, the solvent molecule pass through this membrane and the passage of solvent molecule through the semi-permeable membrane takes place in both directions since solvent is on both sides of the membrane. The solutions passes from more dilute solution to more concentrated solution is found to be greater than the rate in the reverse. Now in this topic we learn both of them, that is the reverse osmotic pressure also, and hence let's start to the next slide. Now for the osmosis and osmotic pressure, let's we see one diagram there. For that we require the semi-permeable membrane. Dear students, first upon we know what is the semi-permeable membrane. The osmotic pressure phenomenon which involves the use of semi-permeable membrane. Actually it is a thin film such as cellophanes like that which has pores and that large enough to allow the solvent molecule to pass through them. These pores are small enough not to allow the passage of large solid molecules or ions of high molecular mass through them. The semi-permeable membrane there selectively allows to passage of the solvent molecule. So it's simple as like the thin film. Now for that we go to the osmosis. What is the osmosis? When a solution and pure solvent or two solutions of different concentration are separated by semi-permeable membrane, which we see in the diagram also. The solvent molecule passes through this membrane. Then one thing must be understand that the passage of solvent molecule through the semi-permeable membrane takes place in both directions. Since solvent is on both sides of the membrane, the rate of passage of solvent molecule into the solution or from more dilute solution to more concentrated solution is found to be greater than the rate in the reverse direction. Dear students, remember one thing, that the solution should be passed from more dilute solution to more concentrated solution is found to be greater than the rate in the reverse direction, and this is favorable since the vapor pressure of the solvent is greater than that of the solution. The net spontaneous flow of solvent molecule into the solution or from dilute solution to more concentrated solution through a semi-permeable membrane is called the osmosis. Is it clear? So the net spontaneous flow of solvent molecule into the solution, spontaneous continuous flow from the solvent molecule into the solution or from more dilute solution to the more concentrated solution through semi-permeable membrane is called the osmosis. So what happen? The amount of liquid on the pure solvent side or more dilute solution side is get decreased, and hence the amount of liquid on the other side it get increased, and hence in all total there is a decrease of the concentration of solution. So this method is also useful for decreasing the concentration of the solution. Now on the other side it's showing one diagram. That diagram is indicate that the osmotic pressure. So osmosis can be demonstrated by the experiment. Now the semi-permeable membrane, it is firmly fastened across the mouth of thistle tube. Now the solution of interest is placed inside an inverted thistle tube. This part of the tube and the membrane are then immersed in a container of pure water. So what happens? The result across that some of the solvent get passes through the membrane into the solution, and that cause the liquid level in the tube now it get rise. The liquid column in the tube, it creates hydrostatic pressure that pushes the solvent back through the membrane into the container. The column of liquid in the tube now it continues to rise. Of course, why? Because the solution, the pressure is applied on it and eventually stop the rising. At this stage, the hydrostatic pressure is developed is sufficient to face the solvent molecule which back through the membrane into the container. At the same rate, they enter into the solution. So an equilibrium is thus established in between objects, that is the rate of forward and reverse passage, they are equal. So the stage is at the equilibrium. The rate of the forward is exactly equal to the rate of the reverse, and hence the passage they are equal. Therefore, the height of liquid column into the tube, it remains constant because there is no any change. Whatever the pressure we apply for the forward, same we required for the reverse, and hence there is no increase in the height of the liquid. This implies that the hydrostatic pressure has stopped the osmosis. What is that hydrostatic pressure that stops the osmosis? It is known as the osmotic pressure. That pressure is the osmotic pressure, which is equal to H rho G, where H is the height of liquid column, rho is the density of the solution, and G is the acceleration due to gravity. So that osmotic pressure is showing the hydrostatic pressure that stop the osmosis, which is an osmotic pressure. Now I just told that the osmotic pressure, which indicates by the symbol pi, and the hydrostatic pressure, which is equal to H rho G. Now here the H is showing the height of the liquid, rho is the density of the solution, and G is the acceleration due to the gravity. Now we learn that what is the solution and how the solvent and solid molecules can be present in the solution. According to that, the types of solutions based on the osmotic pressure. Now isotonic solution, hypertonic solution, and hypotonic solution, these are the three types. I repeat once again: isotonic solution, hypotonic solution, and hypertonic solution. So we write here in the distinguished form, but the definitions are most important. Iso means same, tonic means osmotic pressure. So in the first case, isotonic means what? They are having the same osmotic pressure, two or more solutions having same osmotic pressure. While hypotonic, a solution hypo, now here hypo means lower, hyper means higher, a solutions having osmotic pressure lower than that of another solution, which is known as the hypotonic, and hypertonic, which indicates that a solution having higher exerting osmotic pressure than other solution. Now if we take the example of isotonic solution, good example is if we take the urea and sucrose both having the same concentration, that is the 0.05 molar urea and 0.05 molar sucrose solution, both having the same osmotic pressure, and hence it is the example of isotonic solution. Now here one thing is remember that solutions having the same molar concentration but the different concentrations in gram per liter. If these solutions are separated by semi-permeable membrane, then there is no flow of solvent in either direction. After that, hypotonic solution, in which example is that 0.05 molar sucrose, which exerts lower osmotic pressure than 0.1 molar of urea. Now dear students, you can understand here there is a difference in the osmotic pressure of the solution, which showing last condition they are showing the higher than that of the urea solution. The sucrose solution is the hypertonic solution to urea solution, and the urea solution is hypotonic to sucrose solution. That is the small difference in between of them. So the concentrations are different but the molality should be the change, and according to that the sucrose can exert lower osmotic pressure than 0.1 molar urea, while in the hypertonic 0.1 molar urea which showing the exerts higher than that of the 0.05 molar sucrose. According to that, the classification of solutions is based on the osmotic pressure. Now the next and most important term is that the osmotic pressure and concentration of solution. Just now we learned that the types of solution, which is how it can be based on the osmotic pressure. So for dilute solution, very dilute solution means it contains very little amount of the solute particles and more amount of the solvent as a water. The osmotic pressure which follows the equation pi is equal to N2 RT upon V, where V is the volume of solution, of course in dm cube, which containing N2. N2 means what? Moles of non-volatile solute, which we learn in the Raoult's law. R is the gas constant, which is equal to 0.08206 dm cube atmosphere per Kelvin per mole, and pi is the osmotic pressure. Just we learn. The term N2 upon V is the concentration in molality, and hence just put the value of that molality N2 upon V, we showing the molar mass, that is molality. So what we write there, pi is equal to MRT. Now here M is indicated as the molarity, not a molality. So the solute concentration is expressed in the molarity while calculating the osmotic pressure rather than molality. The reason is that the osmotic pressure, which is measurable at specific constant temperature, and it is not necessary to express the concentration in temperature. So all of you know that it is a temperature independent unit like the molality. So we consider here molarity, not a molality. So molar masses of solute from osmotic pressure, just we revise that the pi is equal to N2 RT upon V. Now N2 upon V we consider here the molarity, and now we write there M. So according to that, if the mass of solute in V liter of solution is W2 and its molar mass is M2, then N2 is equal to what? W2 upon M2, that is the weight upon mass. Substitute this value in the given formula. So what we get? Pi is equal to W2 RT upon M2V, or if we take the term M2 comma M2 outside, so what we write? M2 is equal to, just cross multiply, M2 is equal to W2 RT upon pi V. According to that equation, we can solve the number of the numericals, but once again I remind that the numericals will be solved on whenever our college will reopen. Now the remaining part, that is the reverse osmosis and small term is remains, that part we learn on the next lecture. Thank you.